So what did you notice, depending upon which side of the mirror you had?
It zoomed or made it smaller. Yeah.
Okay, so on one of them, did you notice that you could flip the image over? Okay, so on one side you could flip the image over, and the other side it never flipped over, right? So that's what we're going to start with. So the reason I'm going to start with this concave mirror, and we're going to spend a lot of time kind of going through this whole thing, and you can see how the ray tracing diagrams work and things like that. So I'm going to go through, and this is going to take a while, okay, because it's going to take some complex drawing to make this all happen. But what you've got to be able to do is see the pattern in terms of this, what's called the thin lens equation. So this thin lens equation is, you always have three different things. You have, this is what's on your sheet. So all this is the same file, or the same sheet of paper that you have. So you have three different things that you're going to deal with, okay? SO, and it doesn't make any difference. The beauty of this equation is that it's the same equation all the time. You're always going to have these three variables. So it isn't like we have one thin lens equations for mirrors and we have another thin lens equation for lenses, okay? It's the exact same thin lens equation. So basically, if you look on, somebody have their equation sheet?
Yes.
So your equation sheet on your book is a little bit different. Well, no, so they actually changed it. It used to be wonky. So they got 1 over psi plus 1 over so equals 1 over f. So your SI is going to be the distance to the image. And usually this is what you're trying to solve for, okay? Usually it's your image distance that you don't know. So SO is the distance to the object, and F is the focal length. Now, there's a couple of things, and this is going to be all about sign, okay? So when you look at this, your object distance is always going to be a positive number. Okay, there's no variation on that. So this object distance doesn't make any difference whether it's a lens, converging, diverging, doesn't make any difference. Your object distance is always going to be a positive value. Your signs of your image distance and your focal length can be positive or negative depending upon the situation. So here's the deal. With that focal length, okay, and that focal length isn't, here's the common misconception that people have. Your focal length is not where the image is going to appear. Your focal length is a property of the lens itself or the mirror itself, okay? So like, we're gonna go back to the back here in just a second. And it'll say, hey, it's a 20 centimeter convex lens, okay? That 20 centimeters is referring to that focal length. It doesn't necessarily mean that's where the image is going to be in focus, okay? So I want to get that straight right now. So just because the focal length is 10 centimeters, that doesn't mean that's where you're going to form the image, okay? Most of the time, you don't form the image where the focal length is. Sometimes you can, but that's pretty rare. So I want you to get out of your minds right now that your focal length is not where you see the image. It's a property of the mirror or the lens itself, okay? Got that? Good? Great? Fantastic. Now, your focal length can be positive or negative depending upon the situation, and that's what I tried to explain back there. So if that mirror or that lens is bringing the rays together, that's like someone that has a positive personality, and your focal length is going to be a positive value. If the rays are being spread apart, and that's divergent, that tends to be a negative personality, and the rays, and that's going to be a negative value. So your focal length can be positive or negative. Now, your image distance, you'll see, can also be positive or negative. And this will make sense once we kind of go through some of these. But if your image distance is negative, that means it's in the opposite direction that the light is traveling. If your image distance is positive, it's in the same direction that the light is traveling. It'll make sense. That seems nebulous. It'll make sense once you kind of see some examples. Okay? So here's the easiest way to start 99% of these problems. Your object distance is going to be a positive value. You decide the value of your focal length, whether that's positive or negative, and it won't tell you. Okay? Typically on these problems, it will just say, hey, this mirror has a focal length of 20 centimeters. You have to decide if you're going to make it a positive or negative value. Okay? So typically they don't designate it as a positive or negative value. It's just going to say, hey, here's this focal length. Okay. So we're going to start with this convex mirror. So typically what you're going to do, good luck, fellas.
Bye, gents.
So typically you're going to pick something that you're going to draw that has like a top and bottom to it. Traditionally, your object is a candle because that's what they did the initial room with, because they didn't have light bulbs and they used candles. So typically you'll see this as a candle. I don't recommend that you just use a line, mainly because of the fact that if you just use a line, then you can't tell if it's the top or bottom that you're looking at when you get done. Okay? So if you use something that has some type of top and bottom to it, the number 7, the number 4, arrow, a candle, I don't care, okay? A squirrel, it doesn't make me any difference. Squirrels would be tough to do, but you can do that, okay? I don't recommend it because you're going to spend a lot of time drawing squirrels. Okay. Now, typically, you can figure out where the image is going to be based upon 2 lines. Typically, you want 3 just to make sure. And again, this just comes with experience in terms of how these are drawn. So typically what you're going to do is that, like in this situation, I'm going to tell you that this object distance is 40 centimeters away. So what's going to happen is that I'm going to have a convex lens with a focal length of 20 centimeters on it. And I'm going to put this candle 40 centimeters away from that. Good with this. So now the first thing that you have to decide is you've got psi, and your focal length. Your object distance is always going to be a positive number. So that's going to be positive, and I'm going to make that 40 centimeters. Now, my focal length is 20 centimeters. Okay? That's just a number. So what I have to decide is that am I going to make that focal length a positive or a negative value? So which is it going to be?
Positive. Negative? Negative.
Negative. Because look what happens. When these rays hit this mirror, they spread out.
Oh.
Okay? They diverge out from that. Okay?
I was looking at the dashed lines.
Yeah. So now we'll get to the dashed lines in just a second. So my focal length then is going to be a negative value. So that's going to be a negative 20 centimeters. Okay? Good with this.
How do you
Now,
tell if it's negative or not?
what I'm trying to figure out is what's my image distance. So I'm going to show you how you can do this mathematically, but then you also, the most vital skill that you also have to have is the ability to draw these diagrams, okay? This isn't just slamming numbers into a calculator. You also have to be able to draw these rays to figure out where this thing is going to go. So let's start with the math part of it. So I know psi, that's going to be the image. That's what I don't know. I know my object distance and I know my focal length. So how this usually works from a more practical standpoint is you're typically searching for psi. So typically how you do this most of the time is that it's 1 over focal length minus 1 over your object. Okay, that's how you're going to do probably 95% of the thin lens equations, is that you're trying to figure out the object or the image distance. That's usually what you're trying to find. Now, so in this situation, and if you're not good at inverses, you'll get good at inverses. So in this case, I got a focal length which is negative 20. So I'm going to take 1 over negative 20. And that negative sign is vital. Minus 1 over my object distance, which is 40. And then I'm going to take the inverse of that, all of that, to get my actual image distance. So you subtract the inverses. Then when you get that answer, then you flip it over. Okay, don't flip it over. Don't take negative 20 minus 40. Okay, and then flip it. No, bad. Okay, so you somebody take 1 over negative 20 minus 1 over 40, and then flip that.
Negative 13.3.
Okay, so you get negative 13.3. So that's what we get, negative 13.3?
Yep.
Okay. We're good? Okay. So what that tells me is that this image is going to be, because that's negative value, it's going to show up on the other side of the mirror. So what's happening, and now that you can look at this, so the light is coming in this way, but what I'm going to see is in the opposite direction of the light. So the light's coming in, like on this diagram, is moving to the right, okay? But the image is going to be on the opposite side of that mirror, okay? So that's the mathematical side of it. So here's going to be the next big thing that you need to know, and that's HO and HI, okay? So HO is your object height. So in this situation, I have like this 2 centimeter high arrow. And then I've got, what I'm searching for is my image distance. And then I've got my magnification, and is it upright or is it virtual? So here's the deal. So on your equation sheet, if I may, and I don't know why they do this, they'll just, so on your equation sheet, they've got the formula for your magnification. That got all weird. So the magnification, there's 2 ways, and they do absolute values, and I don't know why. But it's high over ho and psi over so. Okay? So that's what's on your equation sheet. So, but in reality, this, like I said, I don't know why they do this, because usually if you can figure out the sign of your magnification, it's going to tell you if it's upright or inverted. So this is what's on your AP sheet. I wouldn't worry about the absolute value of it, because it actually makes it easier if you don't worry about the absolute value of it. I've never figured out why they did it that way. It's the only time I've seen in all my studies where they do this. Personally, I wouldn't worry about the absolute value, and you'll see why.
So the magnification can be negative?
Oh, yes.
Okay.
But that's why they have the absolute value, but I don't like the absolute value part of it. That's just me. Okay, I don't take the absolute value of it because I want to see if it's negative or positive, and you'll see why in just a second. Okay, so in this situation, I know my psi and I know my so. So in this situation, my image distance was negative 13.3 centimeters, and the object distance was 40. So somebody take 13.3 and divide that by 40.
0.33.
Okay?
3.
Negative.
The equation on it has negative.
But with this one, so my object distance is 40, so this is going to be negative 0.33. So if your magnification
What about this equation that says negative SI? Yeah.
Oh, that is right. There is a negative on, that is
So
right.
The negatives cancel out. So
Yeah,
that
the
gives you a
negatives
positive.
cancel out. I forgot about that.
Oh.
My bad.
Okay.
So,
It's positive.
yeah, it is positive. I forgot about that extra negative in there. So what I've written on your sheet is there's like an extra negative in there. And so I realize that makes it more complicated, but it'll make sense in just a second.
Is that true of all equations or just that specific one?
No, just for all magnifications, on that particular
So it's always going
magnification.
to be m equals negative psi over so.
No, it would be two.
Wait, say that again?
We'll get to it. Just
I'm confused.
stay with me
Thank
here.
you.
Okay.
SISO.
So, here's the deal. Yeah, it's got a negative on both of them, okay? So, this works out to be 0.33. So that magnification, if it's less than 1, that means the image is smaller than the object. If your magnification is equal to 1, they're the same size. And if your magnification is greater than 1, then it looks bigger, okay? Makes sense. Okay, so I've got a positive 0.33 as my magnification, right? Now, because I've got a positive 0.33, so that's going to be 0.33, okay, on that magnification. So is it upright? Yes, okay, because what I'm going to look at in the mirror is that I'm going to see an upright image, which is cool, okay, because if you look on the mirrors in your car, especially on the passenger side, those will be convex mirrors. I don't want to look in the mirror on the side of my car and see the truck beside me upside down, okay? I want that to be upright. Now, here's the other thing that they will tell you. If you notice on your passenger side mirror, it'll say, objects in mirror are closer than they appear. Because when you have a convex mirror, the image that you see is smaller. So here's the situation. It's like you see this semi in the back of your mirror and it looks really small and you think, oh, it's a long way away because it looks small. In reality, it's much closer to that mirror than what it appears. So that's why your rear view mirrors have that warning on there that says, hey, they're closer than what they actually are. Okay? Good with that. Okay. Now, here's where you get into the drawings. Okay. Now, when you actually do these, you guys will actually do these to scale, and I'm going to go old school, and I'm going to use a candle, okay? So, in this situation, I've got this thing at 40 centimeters away, so you're going to set up a scale, okay? I doubt that you're actually going to draw it 40 centimeters, so you might let like 5 centimeters equal a meter, something, or a centimeter, something like that. So, this is going to be my SO. I've got a focal length of 20. So typically with mirrors, you put focal lengths on both sides. So here's the easiest one to draw on any mirror. This is the one that I always draw first. So come in here and you're going to draw a line from the top of whatever this thing is straight through to the middle of to this point. So you're going to catch the very top of this, have it come down here, hit this, what's called the prime axis, okay, your center prime axis. Have it hit this point right here. Now, what I always do is that I don't even care what this length is. I just always flip this over. So like if this is 2 centimeters, I come directly below that and make a mark that's 2 centimeters. Then I'm going to bring this line directly back here. So at this point, here's what I've got. The reason that we use dashed lines is because if your eyeball is here and you're seeing it, because this is where your eyeball is looking, it's going to look like it's coming from this point up here. So that's why we put those dashed lines on the opposite side of the mirror, so that that's what it looks like. So it's bounced off here, but to our eye, it looks like it's coming from the other side of the mirror. So that's always the easiest one to draw, is flip that over, have that go through there. Now, here's the other one that's easy to draw. Take this line and bring it parallel with the line. And this one you've got to use the focal length that's on the other side. So then you take this line through that focal length to there. So even though this focal length is on the other side, what's happening is that this line is going to hit, and it's actually going to bounce off, and it's going to go like this. Okay? So technically, this should be a dashed line here. So at this point, what I have is that I've got two lines that are going to tell me where this image is going to be. This is one of them right here. Okay? So this is with mirrors, this is always the easiest one to do. Whether it's concave or convex, it doesn't make any difference. That's always the easiest one to draw. So then, with this one, you bring it in parallel. It's going to bounce off here, but it's like it's emanating from the focal point that's on the other side, if that makes sense. So that's why this is a dashed line. So at this point, what I've done is that I've begun to establish where I think this thing is going to be. Okay? All right. Now, at this point, you can kind of get another one if you wanted to. Now I got to remember. Hold on. Oh, yeah. So if you try and send one, this one's the hardest one to kind of see. Okay. So if one comes in like this, and it would try to travel through that far focal point there, it's going to hit, and then it's going to bounce and run parallel with it. So this one is trying to send it through this focal point on this back side. It's going to hit this surface, and then it's going to run parallel with it. So then this establishes that third line. Ideally, you would draw 3 rays to make sure that you know exactly where it is. If you're really good, and you're feeling confident, you can get by with 2. But the 2 easiest ones to draw are always going to be on any mirror, comes in, hits, gets flipped. This one, boom, this is that focal length. There's your other one. So what's going to happen is that what you're going to see, it's going to look like it's on the other side. So if you've still got that convex mirror, when you hold it up, okay, you're going to see you're going to look small, because what's happening is that light is being diverged out. So what you're seeing, though, what's striking, because your eyeball is out here, okay, this is what your eyeball is catching, is the refracted light. So it's going to look like it's coming back to this point right there. Okay? Makes sense. Okay. All right. So I know you've been sitting, so stand up for a second. Take a stretch. I've got to go, like the insurance people just called again. I got to go make, it's a long story. I'm fighting with insurance companies. I got to go make a real quick call to an insurance company. I'll be right back.